Now let's get into differentiating the natural log function, the derivative of the natural log function. I'm going to show it to you guys this way. The definition of the natural log function can be written as the natural log of x equals the integral from 1 to x of 1 over t dt when x is greater than 0. If I want the derivative of the natural log of x, I would write it as such. d dx, the derivative with respect to x of the natural log of x, equals, so if I did d dx of this side, the derivative with respect to x, I do the derivative with respect to x of the other side. So I'm going to write it that way. And we remember from the second fundamental theorem of calculus that if I'm doing the derivative of an antiderivative, those are inverse processes, our shortcut is that they can cancel each other out, but in the process we know that that variable gets plugged into where that variable is. If we were to do it the long way, we remember when we did it the long way, why that happens. So ultimately, we know that the derivative with respect to x of the natural log of x equals 1 over x. There's other reasons we can look at for why that's true. Ultimately, though, we need to remember that. Now we know ultimately that it's not just going to be all the time just natural log of x. It's going to be natural log of, who knows, some other expression. So let's think of what if it is the derivative with respect to x of the natural log of some other expression. I'm just going to call it u to keep it basic, but it could be 5x plus 8x squared minus 3xy. You know, it can be more than just x. So here's what we look at when it's more than just x. We think of our chain rule. So the derivative of the natural log of x is 1 over x. The derivative of natural log of u is 1 over u. But if it's with respect to x, we say times, using the chain rule, the derivative of u, whatever that function is, with respect to x. Remember, that's our inside function, or our outside function. The derivative of natural log of u is 1 over u, the inside derivative du dx. Well, another way that we can think to write this, 1 over u is the derivative of natural log of u, so 1 over u is the derivative of natural log of u. Du dx can also be written in shortcut form as u prime. What I'm trying to get at is that a lot of times you're going to see it simplified, the derivative of natural log of u, to just u prime over u, instead of writing it as 1 over u times u prime, just u prime over u. Ultimately, you need to memorize that the derivative with respect to x of the natural log of, we're going to call it absolute value of u, and I'll explain in a minute why, is u prime over u, the derivative of what's inside over what is inside. This is our bottom line here today that we're going to use. Memorize this guy. Let's take a moment and talk about why we're saying the absolute value of u. Remember that the domain of the natural log of x, if I'm going back to what that graph is, that's only for x values that are greater than 0, between 0 and infinity. So if I have any x values that are negative, I can only plug them in if the function says natural log of negative x. So let's look for a moment at the derivative with respect to x of the natural log of x. I'm going to write it differently. The derivative with respect to x of the natural log of x, we remember that's 1 over x, or the derivative with respect to x of the natural log of negative x. Well, the derivative of negative x is negative 1 over what's inside negative x, equals 1 over x. Notice they are the same thing. Ultimately, when we get to antiderivatives, we want to know, well, what happens when we see 1 over x? Which one is it? Well, because it could be both of them is part of the reason, we're going to include them both in the absolute value. So we say the derivative of the natural log of the absolute value of x is 1 over x. Or better yet, we say the derivative of the natural log of the absolute value of u, since we know the inside could be anything, is u prime over u. Let's practice using that derivative. So I take in what's inside the natural log function, and often I really, with my natural log functions, because of the properties, I really want to think to myself first, can I simplify by expanding? That's what I ask myself every time I come to a natural log problem. Can I simplify first by expanding? I'm adding expressions here, so no. Multiplying, dividing only can split it up. So I can't here. So I go straight into my derivative dy dx equals, and I think to myself, the derivative with respect to x of the natural log of whatever is in there is the derivative of whatever's in there over whatever's in there. Or the natural log of u turns into its derivative is u prime over u. Doesn't matter if there's absolute value symbols there or not, it's u prime over u. So the stuff that's inside my natural log, I'm thinking of that as my u. Its derivative is 2x, and the u that I look at there is x squared plus 3. Of course, I always want to ask, can I clean it up? And here there's no simplifying, so I'm done. Take a look at another one. Perhaps you pause the video, try it, come back. Forget about the fact that there's absolute value symbols there. Whether there are or not, remember we get the same thing. Quick flashback, remember positive x, negative x, same exact answer. So absolute value, same exact answer. Okay, let's go back. The 5 is just a coefficient. Keep it in front while we deal with everything that comes after. The u is the stuff inside. Its derivative is cosine of x over itself, sine of x. Leave it like that if you like, but we know that that can be cleaned up. And for reasons of stuff we're going to do later, we want to think of cotangent antiderivative. We're going to be getting there soon. This is our final answer that we want to write down, select, and we're good to go. How about this one? Looks kind of tricky because there's two natural logs. Just take your time and think of what is in this natural log function, this stuff. So this is my u. Perhaps off to the side you say, well, this is my u, natural log of x. What is u prime? The derivative of natural log of x is 1 over x. So now when I go to what is dy dx, and I think to myself, oh, this is a natural log function, so u prime over u. Of course, we won't forget about the coefficient of 2. It becomes 2. U prime is 1 over x. U is natural log of x. Well, this is an answer, but this is an ugly answer. We don't want fractions inside fractions, so let's clean this up a bit. How about 2 times 1 over x, this guy that was on top, times, instead of divided by, times the reciprocal of natural log of x. This is looking a little bit better, but I know we can do better than this still. 2 can be in our numerator over x natural log of x. This is our best answer. Now, you know I don't normally circle answers, but I want you to give me the most cleaned up answer you can in cases like this. Let's look at another one. I picked this because, yes, we could go straight into u prime over u. However, I see something that, can I simplify by expanding? Can I do that first? Remember, I think of that first. Here I can. So if I can, I like to. So I'm going to rewrite this as 2 natural log of x. Then I'm going to do the derivative. dy dx equals 2 times the derivative of natural log of x, 1 over x. And I'm done. Perhaps make it a little bit easier by calling it 2 over x. Not a little easier, but a little more cleaned up. Now here's some examples where we have to expand first. Otherwise, it's just ridiculously, unnecessarily more complicated. So in a problem like this, where I have the y stuck inside the natural log function, I really do want to expand it first. and we will be using implicit differentiation. Let's see how this is going to work. So my property of expanding gives me natural log of x plus natural log of y equals 2x. Now I can't get the y by itself, so now I differentiate implicitly. What's the derivative of natural log of x? 1 over x. What's the derivative of natural log of y? 1 over y dy. I said y and I didn't write y. 1 over y dy dx, or y prime over y, equals the derivative on the other side, 2. Now I pause for a minute because if you're writing y prime and you're writing y, sometimes those can get a little bit mixed up. So perhaps instead you write it as 1 over y like I did at first times dy dx. I kind of prefer it that way because then I don't accidentally miss the prime symbol and think of these as like y over y. Now I need to get my dy dx by itself. So we'll start by subtracting the 1 over x, and then end with getting rid of the 1 over y, which means we have to multiply by y. So 2 minus 1 over x times y. And that's looking pretty good from where we're standing here. Let's take a look at this expression. Again, I will think when I see something this complicated, expand first. So thinking of my expanding properties, I'm not doing a derivative, that's why I can say equals. Natural log of, now cubed root, think of it like it's exponent of to the 1/3. Put the 1/3 out in front of the natural log. So I didn't give myself much room here to do that. And it doesn't have to be the first thing I do, but it's the most outer thing that I see. So it kind of makes sense to do it first. What you need to be careful of is now when we're using our dividing property, we have the 1/3 out of all of it. Natural log of x minus 1 minus the natural log of x plus 1. Now we're ready to differentiate. So now I'm going to say dy dx equals, I've got a coefficient of 1/3, so 1/3, big brackets. Now I look at my first, and I think here's my u inside the x minus 1. U prime is 1. U is x minus 1. Notice how there's no natural log in the derivative. Minus, over here, next expression, the u is inside x plus 1, so its derivative again is 1 over x plus 1. And those are all those natural log expressions, and I have a derivative. And this is fine, this is nice, but we can simplify a little bit more, and I should clean it up a little bit. Especially if I'm going to have a multiple choice, this would usually not be an option. So let's get a common denominator first. X plus 1 is needed in this one, and in this one, x minus 1 is needed. So we'll multiply by each other's denominators. We have x plus 1 minus x minus -1 makes plus 1. So there's what we have in our numerator over x plus 1, x minus 1 turns into the difference of squares, x squared minus 1. Looks good. Don't forget about our coefficient, 1/3, and let's take it a step further. X minus x, 2 1s make 2, so we've got 2 over 3 x squared minus 1. That looks pretty cleaned up to me.